So now we're going to talk about the Chapter 3 practice test. In fact, I'm just going to go over it. So here we go. Using graph utility, construct a table of values for the function. Don't worry too much about that. Then sketch a graph of the function, identify any asymptotes and intercepts. So looking at 10 to the negative x, there's two ways to go. Remember, negative exponents take the reciprocal. That's 1/10 to the x. So what that is exponential decay, or you can recognize the negative exponent is going to reflect 10 to the x, which would go like this, over the y-axis, so it'll go like this. So when we're looking at this, it's going to look like that, right? It's going to have an intercept at, well, 1, because if you plug 0 in, if you plug 0 in for x, you plug 0 in for x, 10 to the 0 is going to be 1. So we know what the y-intercept is, 0, 1. So you can just label that. That answers that question. Any asymptotes? It's got a horizontal asymptote, as we know, at y equals 0, because it hasn't been shifted up or down. Okay, same idea here. We've got 6 to the x in the basic form, which is an exponential growth model, but a couple things have happened. First off, under normal circumstances, it would have a y-intercept of 1, but the problem is it's been shifted to 2 units this way. So this x minus 2 here shifts it 2 units this way, and this negative sign here reflects it over the x-axis. All right, so what we're going to do is we're going to sketch this. So it's exponential growth that's been shifted 2 units this way, so it's going to go further that way. Then it's been reflected. So it's going to end up looking kind of like this. So it turns out the horizontal asymptote is still y equals 0, right? The hard part is figuring out it's not hard. The more difficult part is to figure out what this is, because there's an actual gyrations to this. So what we need to do is we're going to figure out the y value when x equals 0. So y equals negative 6 to the 0 minus 2 would be negative 2. So what does that mean? Well, what is that y value? So that is the negative. Remember, negative exponent takes reciprocal and squares it. So that's negative 1/36. So it turns out that the y-intercept, that is when x equals 0, is at negative 1/36. If you think about it, 1 is going to be around here, and so if you shifted it back, it would be there, but it's been shifted this way, so we're shifted into the smaller regions here, okay? This one's a little bit trickier, but remember that e, especially e to the 2x, e squared, right? That is going to be what? Well, e squared itself is going to be much, much larger than 1, so this is going to be exponential growth. But it's also been reflected, the negative, so that's reflected over the x-axis. So it's exponential growth that's been reflected, so it's going to kind of look similar to this. And 1 means it's also been shifted up 1. So under normal circumstances, it would level off at 0 like this one does, but if it's been shifted up, then it's going to level off that way, right? Now, I'm guessing that this is at 0, 0. We're going to verify that here in just a sec, but we know that this point is 0, comma, I'm guessing 0, but we'll verify in a sec. Let's do the horizontal asymptote, which is at y equals 1 because it has been shifted up 1 because of that. Remember, this is same as saying this plus 1, okay? So we're going to do the same thing. Y equals 1 minus, that is, we're finding the y-intercept, e to the 2 times 0 or 0. Anything to the 0 is 1. 1 minus 1 is, I was right, it is indeed 0, which kind of makes sense because normally it'd be 1, but if it got shifted up 1, so it would be negative 1 because it was reflected, it got shifted up 1, so it's then 0. All right, evaluate the expression. Don't blink, this is going to go quickly. Log base 7 and 7 are inverses. Composed means they cancel, so the answer is negative 0.89. Or 7 to what power equals 7 to the negative 0.89? That is, I could say this equals question mark, right? And write an equation. Same idea here, except I have 4.6 times, what's the natural log of e squared? E to what power is e squared? 2. Or the natural log and the e cancel. So this answer is 9.2. That's what 2 times 4.6 is. 5 minus, so let's look at this. Log 10 of 1,000 equals what? 10 to what power is equal to 1,000? Well, to get 3 zeros, that means question mark has got to be 3, which means that this whole mess is equal to 3. So my final answer is 5 minus 3, or 2. All right, find the domain, vertical asymptote, x-intercept of the logarithmic function, and sketch its graph by hand. So remember, these are reflections over the axis, so in general, they're going to kind of look like this, right? So the domain, unless there's something funny going on like there is here or here, is going to be at 0 and greater. So in this case, because it hasn't been shifted left or right, this has not, this is a downward shift, right? This has not been shifted left or right. That means we do what? Well, we can say that this is from 0, non-inclusive, to infinity. Oh, heck, let's do these domains too. So this has been shifted 4 units in the negative direction, right? So normally it would be 0, but it's been shifted 4 in the negative direction, right? Because this is a, right, shift 4 that way. So I would argue that it's going to be a negative 4 infinity, okay? Same logic here, except it's been shifted 6 units this way. Now this is a vertical shift, so that's not going to affect that. It's just shifting that whole graph like this, right? 6 units that way, which means instead of starting at 0, the other way to look at this is, can we take the natural log of 0? No, we can't, so that's our limiting factor. But that means then 6 and higher, right? 6 minus 6 is 0. Anything past that is going to be okay. So that takes care of the domains. Check. Vertical asymptotes. Vertical asymptotes. Vertical asymptotes. What's the vertical asymptote of this? X equals 0. What's the vertical asymptote of this? X equals negative 4. We want to guess what this is. Right? X-intercept. The x-intercept occurs when the y value is 0. So 0 equals negative log base 10 of x minus 6. Add 6, right? And then what? Negative, so negative 6 equals log base 10 of x. This is the same as saying x equals 10 to the negative 6, or 1 over 1 with million. I'm just going to say 1 over 10 to the 6, okay? So the x-intercept is this x-intercept. Same idea here. 0 equals natural log of x plus 4. Remember, this is base e, so e to the 0 equals x plus 4. That's 1 equals x plus 4. X equals negative 3. So the x-intercept is negative 3. Same logic. Before I can rewrite this as an exponential equation, I'm going to have to subtract 1. Exponentiate base e, right? E to the and e to the, so e to the negative 1 equals x minus 6. Now I'm going to cheat. I'm going to add 6 to both sides. Now e to the negative 1 is 1 over e. I add 6. That is going to be my x-intercept. It's a number. So be it. It's a little bit more than 6, right? Okay, x-intercept. Then sketch the graph by hand. All right, so this next part, we're going to take all these things, put them together, and make a sketch. How's that going to work? Well, we got all our information. We know that this is going to look like what, and what. So we want to label key points. We need to label the x-intercept. So 6 plus a little bit. So here's 6 plus a little bit, 6. So the y-intercept is actually going to be here, a little bit beyond, right? What's the vertical asymptote? X equals 6. So it's going to level off there, and it's going to look like that. Right? This is going to be an asymptote. What about this one? Negative 3 is the x-intercept, right? And we know that it has a vertical asymptote at negative 4, so it's going to cross at this point, go like that, there's reflection, and like that. And this one is even more entertaining. This is tiny, right? Small. It's been shifted down 6. This is part of that reason. So this is going to have this at, 1 over 10 to the 6th. And then it's going to have an asymptote of 0. That's it. Okay, evaluate the logarithm using the change of base formula. All right, so I'm going to go ahead and pretend that we don't have a calculator. We could just plug this in. So what do they mean by that? I'm going to use common logs or natural logs, but I take the log of the number divided by the log of the base, right? And if you type that in your calculator, you'll get your answer. Log, and I'll use natural log this time. Natural log of the number divided by natural log of the base. As long as you're consistent, log and natural log, you're good. Log of the number you're taking the log of divided by the log of the base. Can you directly figure out what these are because we have the technology? Yes. Okay. All right. Use the properties of logarithms to expand. So now we're expanding this. Okay. So what's going on here? We've got two numbers being multiplied. So this is going to split out into two logs being added. Now you can't have exponents, so that means the final answer has to have that exponent brought down. So that would be a good final answer. Don't forget to bring the exponents down, people. All right, this next one. Okay, here's what I honestly see. And I see a 5 times this and then divided. So we'll split it into 3. Natural log of 5 plus, we're multiplying, natural log of the square root of x minus, dividing by the natural log of 6. Nothing to be done here, nothing to be done here. This is, and you have to recognize this, x to the 1/2 power. So you do need to bring this, and I'll write that out as, I write the step out. This is really x to the 1/2 power, right? Which means that our final answer, because we have to bring the exponents down, is just that. That's it. Okay, next one. So x times, let's move this over here. X times this divided by that. Ooh, what a mess. Okay, and it's got two things going on. Well, let's see what this looks like. So here I would say we have the natural log of x plus the natural log of the square root of x plus 1 minus, now this is where things are going to get a bit sticky, the natural log of 2 plus the natural log of e to the 4th. Now look, I'm dividing by both 2 and e to the 4th, and if you do it like this, that's fine. If you think carefully, you could distribute the negative, so you're really just subtracting both of these. The reason that these are positive, they're in the numerator, right? So ln x you can do nothing with, but this whole thing is being raised to the 1/2 power, see above, right? So we can bring this down. And we have to bring this down. Now I'm going to do that just to make sure that we know we're taking the natural log of that. Minus, I'm going to go ahead and distribute this. It looks a little bit nicer this way. This, okay. You bring the exponent down, what's the natural log of e? Or natural log and e are inverses, so they cancel. That would be a good final answer right there. Because you should recognize that the natural log of e or the natural log of e to the 4th before you bring down the exponent is going to be just 4. Okay? That's it. Condense, go the other way. Adding becomes multiplying, so it would be a log base 3 of 13y, and there's nothing else to be done. If there are multiples, you must bring them up as exponents first. And when we're looking at subtracting two logs, the analog is to divide within the single expression. And that is your final answer. This next one has a bit more going on. So, natural log of x means we're going to have a single natural log, and I know that that's natural log of x, so I'm going to have a fraction because I have x. I'm dividing by x plus 2, and because this is positive, I'm multiplying this by 2x minus 3. Now, just to be safe, I'm going to put this in a giant set of parentheses. There's nothing else I can do. Don't start canceling stuff out. Don't go crazy on me. This is it. You're done. Okay. The reason that the x plus 2 is on the bottom is because it's being subtracted. Another way to think about that is raised to the negative 1 power, and it's being added. Either way. Solve the equation. Okay. So, well, there's a couple different ways to go. First off, we know that the x is the exponent, and it's a log base 3 of 81. You can take the log base 3 of 81. It turns out to be 4, and you're done. Here, we're talking log base 5 of 2500, which is something you can figure out, equals 2x. So x equals the log base 5 of 2500 divided by 2. Desmos is a beautiful thing. You can just type that in, you have your answer, and that will be that, right? So I can't do those, so I have to do some other gyrations here. $2.430. That's it. Home stretch. Solve the equation. 7 to the 6th equals x. All I did, now 2 ways to go. I could exponentiate base 7 to cancel this out, and there we have it. What is 7 to the 6th? I don't really care. Just leave it as 7 to the 6th. I'm assuming that you can multiply 7 by itself 6 times. This is even easier. 10 to the 5th equals x minus 4. 10 to the 5th is 1 with 1, 2, 3, 4, 5 zeros, or 100,000. Add 4, x equals 100,004. Isn't that exciting? There, a little comma to make it easier to read. Solve the equation algebraically, round your results to 3 decimal places. Okay, so this once again has what we're trying to solve for in the bottom, so I'm going to go ahead and boldly take the reciprocal, which means I had to do it to both sides. Don't be that person. So then I'm going to multiply by 1,025. So I get 1,025 divided by 5, which actually is a number that's going to go in evenly, so I might as well write it out to make life easier, is equal to 205. Okay, so then I can subtract 8. Hopefully you can see what's going on here, because I want to get my exponential by itself. 205 minus 8 is 197. I'm going to take the natural log of 197, and then I'm going to divide that result by 4, which is 3 decimal places. I don't care if you round or truncate, so I'm just going to go ahead and write 1.320. If you rounded, it'd be 1.321, but either way works. This next one is tricky because it fools a lot of people. So first off, there are a couple solutions to this. So my advice is to not add one of these to each side and then divide it out because you miss a solution. Here's a better way. This has a common factor, e to the negative x, which means you could pull an e to the negative x out, and if you did that, you'd be left with a negative x, and what is e to the negative x divided by itself? 1. So this is like a quadratic. When is e to the negative x equal to 0, and when is negative x plus 1 equal to 0? Either one of those will answer the question. So when is e to the negative x equal to 0? Well, if you take the natural log of 0, guess what you get? You get, what is the natural log of 0? E to what power is equal to 0? Wait! Does not exist. Is it possible to take a positive number and raise it to something such that even though it's decay, ever get to 0? No. Hopefully you see this as x equals 1, and that is your answer. You're done. Same idea here. But you must first combine these before you exponentiate. So what are we looking at? That would mean I'm looking at the log base 10, so I'm just going to write log of x divided by 8 minus 5x equals 2. Now, it is log base 10, I know. Then I could exponentiate base 10, that is, cancel the log out. 10 squared is 100, not 20. So then I could multiply both sides by 8 minus 5x. So we add this, so we get 501 x's equals 800. I'm just going to leave my answer as x equals 800 divided by 501. That's it. So this next one is tricky, but not that tricky. Another thing, do you see a common factor between the two? Hopefully you do. You see an x. So you have two solutions. When is x equals 0? That's easy to solve. That's just solved, right? Okay. And then 2 times natural log x minus 1 equals 0, which means natural log x equals, add 1 divided by 2, 1/2, which means I exponentiate base e, so x equals e to the 1/2. Now, this is a natural log equation, so we've got to go back and figure out if we're going to have an extraneous solution. So, can we take the natural log of 0? Wait a second, I don't think we can. Because if we take the natural log of 0, in other words, is there a way to take e and raise it to a power? No. So it turns out that this is an extraneous solution. So we ignore it, which means our final answer is just e to the 1/2. Okay, actinium, fun thing, is about 22 years. What percent amount of radioactive actinium will remain after 15 years? So actinium, in terms of time, is going to be some amount of initial actinium times 1/2 to the t over 22. Now here's where it becomes fun. What percent remains after 15 years? This would represent 100%. So we want to know after 15 years what the percent is. So we could plug in 15 which equals our initial amount of actinium times what? Well, 1/2 to the 15 divided by 22 is 0.623, 0.623. 0.623 of this. So 0.623 of the initial amount of actinium. In other words, this, what we're multiplying by, represents how much we have left, aka 62.3% remains. So this multiple ends up being the amount that remains. And if you think about it, after 22 years, what remains? Half, aka 0.5, because that's what you get. That's it for the practice test.